Swayam Prabha. Digital India. Educated India.
So welcome back. In the second lecture, we'll be talking about probabilistic and Bayesian models for solving regression problems. So this is sort of a more real problem as compared to the Gaussian mean estimation problem that we were looking at in the previous lecture. I believe you have been, taught linear regression in one of the previous, lectures. So linear regression everyone has seen, right? So what we will be doing in this lecture is that we will look at how to set up regression problems, both linear and possibly non-linear regression problems, using probabilistic or Bayesian models. We have already seen what are the basic components of a probabilistic models, so how we can use those components to build a probabilistic models for solving regression. So just as a background, I'll come to that. I'll come to that, right? So, I think the reasons are similar to what we already saw. We need, basically, we are learning a model here also, so we need some notion of uncertainty in what our model is, right? So we are learning a weight vector in the regression case, right? So we need to know how certain we are about the parameter, the weight vector, right? Also, when we are making prediction, we need to be we need to have some estimate of how certain our predictions are, what is the confidence, in our. Yes. And also we will see that there are some connections. In fact, you can look at the probabilistic models and under some approximation, you can think of those as non-probabilistic models. We will look at all these things, just bear with me. Anyway, so let's start with some background on linear regression. So in linear regression is basically a supervised learning setting where we are given training data in form of n IID training examples that I'm denoting as x and y. And so these pairs are our inputs, basically, inputs and outputs. Each xn is a feature vector in d dimensions, and since we are doing regression, each response yn is a real value. Okay, so regression is real valued response prediction problem. So again, feature vectors are d-dimensional. Capital D denotes the number of features in the input, and scalar is response is scalar. Okay, and when we are doing linear regression, we typically assume a linear relationship between the inputs and outputs, and this relationship is parameterized by a weight vector w, which is again a vector in d dimension, and we say that yn is approximately w transpose xn. So yn is the response, xn is as the input, and the relationship is roughly linear. Okay. So this can also be written as yn as approximately equal to sum of wd times x and d. X and d is basically the dth feature in the nth data point. Okay, so this is the relationship between the input and output of the nth training example. So this holds for all the n data points. Okay, so this is basically a linear model. And as I said, w, which is basically a d-dimensional vector, is the regression weight vector, and this is the unknown that we will be trying to estimate. So how do we estimate this is what we're going to look at. You can also think of the weight vector, w, so as something where the dth component is telling us the importance of the dth feature in the data. So wd is how important the dth feature is in making the prediction. Okay. Now, if you have seen the non-probabilistic model for solving regression, we typically define a loss function, which can be both either an unregularized or regularized. Okay? So if you have an unregularized loss function, you basically have a least squares objective. Okay? So you solve for the optimal w by solving this least square problem, where the loss function is defined as the sum of squared errors of the truth yn minus the prediction w transpose xn. Okay, and you have a squared here, and this is the loss function on one data point, and you have a summation over all data points. So this is your objective function or loss function, and you find the optimal w by minimizing this objective function with respect to w. Okay. Again, in order to solve for w, you have to take derivative with respect to w, set it to 0, and then that gives you the solution. You might have seen this solution in the previous lectures. The solution has this form. It's basically sum over all the data points, xn transpose inverse, sum of all data points, xn times yn, which also has this matrix vector notation, x transpose x inverse x transpose y. Okay, so I believe if you have seen linear regression, this is the final solution. So the solution is x transpose x inverse x transpose y. So note that this capital X is the n by d data matrix consisting of all the So think of X as a matrix where each row is an example. Okay, so capital X is this n by D matrix, and this bold-faced Y is the vector of all the responses. So this bold-faced Y is then n by 1 response vector. Okay, so this will give you the solution for the weight vector W. Okay, so I believe you have seen this expression before. Raise your hand if you have not seen it. Yeah, I trust everyone has seen it. Okay. So note that this requires an inversion. So X transpose X will be a D by D matrix because X is n by D, so X transpose X will be a D by D matrix. So the result will be a D by 1 vector. This is the D by D matrix inversion times basically X transpose Y. So the overall result will be a D by 1 vector, column vector, which is what your solution will be. Okay. So this formulation doesn't have any regularizer. Okay. You can also come up with a regularized version of the same problem where you add this L2 regularization, where you have an extra term of the form W transpose W, and you add a regularization constant tau, okay? Or sometimes you just use a lambda here, okay? So again, raise your hand if you have not seen this regularized version when looking at least square or linear regression. You have seen it, right? So this is a minor variation from the first case, where you have this additional term in the loss function, W transpose W. And if you solve for this objective, you get a solution that looks something like this: X transpose X plus tau times I inverse X transpose Y. Okay, so we prefer this form because it has a regularization aspect to it, so it can prevent overfitting. Okay, so both. So the first one is unregularized loss function minimization. The second is regularized loss function minimization, where Yn minus W transpose. The first term is the loss function. The second term is the regularizer, and the solution looks something like this. Well, okay. So if instead of a tau, I have no. I think this is like fine. This is tau times I. Yeah. So you can verify this. Okay. Okay, so anyway, so this is the non-probabilistic version of linear regression. So you can solve it, you'll get these solutions. Okay. However, we are talking about probabilistic modeling. So how can we set up this problem as a probabilistic model, and what are the benefits of probabilistic modeling if we solve linear regression using a probabilistic model? So let's first look at the formulation as to how we can set up this problem as a probabilistic model. So essentially, we are looking to design a model where we have an output Yn, which depends on the input and the weight vector. Okay, so you can see. So this picture that I've shown you is a basic, simple, directed graphical model where the direction of arrow shows the dependence. So this arrow pointing towards Y denotes that Y depends on W. Likewise, Y also depends on X. And this rectangle with an N shows that there are N copies of the data. So there are N data points. Okay, every data point has this relationship. Every output has this relationship on the feature vector and the weight vector. Okay. Now we are going to set this up as a probabilistic model, as I said. So we need two ingredients here. First of all, we need a likelihood model, right? If you recall our discussion from the previous session, we had a likelihood model for the observations, and we had a prior distribution over the parameters. What is the parameter here? What is the unknown here? W, right? So W is our parameter, right? So, and what is the observation here? Okay. Now, there can be divided opinions whether our observation is just Y or both X and Y. Okay. Now, it depends on the way you are modeling the data. In this case, we will only model Y. We will treat X as a fixed thing that we are conditioning on, that Y depends on. Okay. So our probabilistic model or the likelihood model will be defined just on Y given X. Okay. In some other models, you can actually model X also, but in this case, we can simply say that we are modeling the predictions, the responses, right? They are functions of X. Okay, so this is also known as a discriminative model. If you want to differentiate with models where we also model X explicitly. Okay. So anyway, so this is the model. So we have a known parameter W that we are trying to estimate. So we will have a prior distribution P of W. We have observations Yn. We will have a likelihood model of the form P of Y given the parameter, right? So note that what is the form of this likelihood? P of Y given the parameter W. Since it also depends on X, so we are also conditioning on X. So this is just a notation that I'm using. Okay, but you can even suppress the X here. You can just say that it's P of Y given X, P of Y given W. But since we are also making Y depend on X, so I have explicitly kept X in this notation. Okay. Yeah. So as I said, we would, in order to set up a probabilistic version of this model, we will specify an appropriate likelihood model, P of y given x comma w, and a prior distribution, P of w. We have not yet specified what these distributions will be. We will be looking at that shortly. Okay. And once we have set up this model, once we have specified the likelihood and a prior, then we can do our basically probabilistic in estimation using MLE or MAP or fully Bayesian inference that we will look at later. And as I was mentioning, in this problem, we will only be modeling the outputs. We will simply treat the inputs as something as given to us. Okay? So we are not modeling the x's, we are only modeling the y's. So in this model, if you think of this as a probabilistic model, only w the parameter and the y are random variables. Everything else is fixed. Note that there may be other hyperparameters in this model. For example, the weight vector itself may have some hyperparameter. Okay? I have not shown that for simplicity. I have assumed that every hyperparameter is assumed to be known, which is why I have just removed it from this diagram. Okay? But we can definitely have more hyperparameters, and as we saw, we can actually have a weight vector depending on another hyperparameter that can be learned. But for simplicity, just focus our attention on only single unknown, the weight vector. Okay, so before we continue our discussion, it's important that all of us see what a Gaussian distribution looks like in more than one dimension. So we have already seen what a univariate Gaussian distribution looks like. So it's also important that we know what a multivariate Gaussian distribution looks like. Okay, so the multivariate Gaussian distribution is a distribution over multivariate random vectors x. Let's say x lives in d dimension. Okay, so suppose you have a vector x, which is a d-dimensional vector. I can define a Gaussian distribution basically to model this vector. And a Gaussian distribution in multiple dimensions can be defined by a mean vector and a covariance matrix, as opposed to a single scalar mean and a variance. Okay, so in the scalar case, we just had a single scalar mean and a scalar variance. But in the multivariate case, we will have a mean vector, which will be a d-dimensional vector, and a covariance matrix which will be a d by d covariance matrix. Okay, and the covariance matrix roughly tells you about the shape of the Gaussian distribution. Okay, so, and the form of the Gaussian distribution is again 1 by square root of 2 pi to the power d times the determinant of sigma times e to the power minus x minus mu transpose sigma inverse x minus mu. Note that this is similar to the quadratic form of the univariate Gaussian, except that we now have this in a matrix vector. So x minus mu is a vector, so we have x minus mu transpose sigma inverse x minus mu and minus half in the front. Okay, so this is the multivariate Gaussian distribution. There are a few properties that this covariance matrix needs to satisfy. For example, it has to be a positive, definite, and symmetric matrix. Also, the inverse of the covariance matrix is known as a precision matrix. Okay, so these are some of the other technical details associated with Gaussians, but I don't think they will be needed here. But the important thing to remember is that this is the form of a multivariate Gaussian distribution. Again, note that the form is quadratic in x and mu, right? So you have x minus mu transpose sigma inverse x minus mu. So x minus mu transpose x minus mu, right? Yeah. So again, it just means that it's a distribution over x with parameters mu and sigma. Okay. So sometimes people use a vertical bar, right? So sometimes people just use a column. So I use it interchangeably. So it simply says that it's a distribution over x with parameters mu vector and covariance matrix sigma. Okay, so now let's talk about the likelihood model. So as I said, in this model, we need a likelihood model for the observations that are y and the parameter that is w. Okay, so let's assume that our probabilistic model is defined as like this. So we will say that our observations yn are defined as w transpose xn plus epsilon n. Okay, so it's again linear function of x plus a Gaussian noise epsilon n, which is assumed to be drawn from a univariate Gaussian with zero mean and a variance beta inverse or precision beta. So beta is known as the precision of a Gaussian. It's inverse of a variance. So if I use 1 by sigma squared, it's known as the precision. So beta is the precision. So beta inverse is the variance. I'm using the precision instead of variance because it just makes the notation slightly simpler later on. Okay. So anyway, so this is our probabilistic model. So we are saying that our observations yn are defined as w transpose xn plus epsilon n, where you can think of this as a noisy version of w transpose x. So you have w transpose x, and then you add Gaussian noise to it. Okay. because the relationship is not exactly linear. So you have a noisy linear relationship, right? So Yn is W transpose Xn plus this Gaussian noise with zero mean. Okay. Now this can also be written as the following. So you can, this is equivalent to saying that the probability distribution of Y given Xn and W is a normal distribution with mean W transpose X and precision beta inverse. And this becomes, apparent from the previous expression, because if epsilon n is zero mean Gaussian with beta inverse, and if I add W transpose X, then the mean becomes from 0 to W transpose Xn. Okay? So the probability distribution over Yn, the response conditioned on the data Xn and W is a normal distribution with mean being W transpose Xn and variance being beta inverse. Okay? So this is the probabilistic view of the linear regression problem, where we are saying that the responses are basically drawn from Gaussian distribution with the mean W transpose Xn and precision beta or variance beta inverse. So what does it mean to have a probability distribution over a response, you might be wondering, right? So typically we think of a response, right? So, but what does it mean to have a probability distribution over response? Well, this picture should kind of give you the idea, okay? Remember that we are doing linear regression for simplicity, right? So linear regression can be thought of as fitting a linear, a line to the data, right? But suppose, our data is in form of these blue dots, right? And we are trying to fit a linear line. Clearly, the data doesn't fall on the line itself, right? So for every x, the points are slightly off from the line, right? So we can think of, each y. So the height of this line, the height of these blue points is basically the y, right? The yn. So we can imagine that each yn is basically centered around. So it's so you can imagine that there is a Gaussian with every data point, and the point could lie anywhere, So this is like I've drawn it in a tilted way, right? So at this point, x star, we have this distribution, and the point can fall anywhere in this line. The mean is, of course, W transpose X, but the point is a random realization from this Gaussian distribution, okay? So it can lie anywhere on this vertical line, okay? Depending on how much the Gaussian is spread. Well, the spread is already defined by beta inverse, okay? So this is what the probabilistic interpretation of this problem looks like. Okay. So as I said, the P of Yn given Xn comma W is our likelihood model. This is clearly a Gaussian. We have already seen that this is a Gaussian distribution. Okay. Note that this is a univariate Gaussian distribution. This is not yet a multivariate Gaussian distribution. The responses are real, right? Yn is a real, right? So this is a one-dimensional Gaussian. The mean is scalar. The variance is scalar, right? So this is, for a single data point, each likelihood is a one-dimensional Gaussian. Okay. So what is the overall? So each likelihood is this term. So what is the overall likelihood? If I talk about P of this bold-faced Y, so this is the notation that I was talking about earlier. So capital X is the n by d feature matrix. This bold-faced Y vector is the n by 1 response vector for all the observations. So if we define this notation like this, then the overall likelihood of our model for the n observations will be a product of the likelihoods of the individual observations. Now, recall that this is similar to how we defined likelihood in the previous, the Gaussian mean estimation case, where since we had the data as IID, the overall likelihood is just a product of the individual likelihoods. Okay, so we have n observations, so we have n likelihoods all multiplied together. Okay. Now, each of these likelihoods is a Gaussian distribution, right? So you have a product of all these Gaussian distributions. Note that this is again a Gaussian. This is a univariate Gaussian. We already have seen a univariate Gaussian. The only thing that is different in terms of notation is that I'm not using sigma squared, I'm using beta, right? So rather than having 1 by 2 pi sigma squared, I have a beta divided by 2 pi. Okay? And rather than having Yn minus W transpose X divided by 2 sigma squared, I have a minus beta by 2. So because beta is 1 by sigma squared. Okay? But other than that, it's just a univariate Gaussian distribution. Okay? So what is our overall likelihood? Our overall likelihood is a product of the individual likelihoods of each data point. So we have a product of many such terms, right? And if I multiply all these terms, exp, the exponents get added up, right? So it will be, okay, so so what are we trying to estimate here? We are not trying to estimate beta. So beta is just a constant. So we can ignore beta, we can think of it as a proportionality constant, right? And then only the second term will matter, only this part will matter. Okay, so this will be e to the power minus beta by 2, and then the square terms will just get added up because this product will turn into a summation in the exponent. Okay, so the likelihood P of Y given X comma W is proportional to e to the power minus beta by 2 times this summation over the squared errors, yn minus w transpose x squared. Okay, this might this already looks like a least square objective, right? I mean, it has the flavor. I mean, the form looks similar to that, right? So by the way, we can also write it. We have a summation here. We can also write it more compactly if you wish, like this. So again, we can write it in a vector notation. So remember that we defined this notation where y is a column vector, x is a matrix. So we can also write the same summation as y minus x times w transpose y minus. So again, I'm using, so as compared to the previous lecture where we were only dealing with scalars, here we are dealing with matrices and vectors. So just like, I hope the matrix vector notation is like not too unfamiliar, okay? This expression is equivalent to this expression, you can verify. Because this is a column vector, y minus x times w is a column vector in n dimension. So you take n dimension vector transpose n dimension vector, so you get a scalar, okay? So this is exactly the same as this. All right, so our likelihood is proportional to e to the power minus beta by 2, then y minus xw transpose y minus xw. So this is our likelihood model, okay? Again, a function of w. W is the unknown here. Now, coming to the prior distribution. So again, our unknown is w, so we have to define a distribution, a prior distribution over w, okay? Why a prior distribution? So why did we use prior distributions in the previous, lecture? Yeah, so what is the role? What is the role of prior distribution? Well, if we have some information about what our parameter looks like, we can impose a prior, we can incorporate that in the prior distribution. Because in the previous case, you might remember, we said that our mu is close to mu 0, right? So we used a Gaussian prior with mean mu 0, right? Likewise, if someone say, likewise, if we expect that we expect the weight vector to have some values, more likely a priori, then we can incorporate a prior distribution. Okay, so suppose that we expect our weight vectors to be, so suppose we expect our entire weight vector or every component of the weight vector to be close to 0, which means that we want the weight vector, the elements of the weight vector to take small values. Okay, in that case, we can say that the prior is a Gaussian prior with 0 mean and some covariance matrix. Again, just to repeat myself, what does this prior distribution, why does it make sense? Or why does it make sense? Well, it makes sense because it's saying that we believe that the weight vector will have small values. Small means like close to 0. Okay? And this is related to the idea of regularization, because when we regularize coefficients, we want them to take small values, right? So the probabilistic way of incorporating the same knowledge in our model is to say that the parameter that we are trying to estimate has a prior that has 0 mean and some covariance matrix, because it's a Gaussian, so it needs a covariance matrix as well. So the covariance matrix has the covariance defined by lambda inverse ID. ID is the identity matrix. Okay. Now, if lambda is large, then what does it mean? Okay, so what is lambda here? What is lambda inverse? The variance, right? Right. So lambda inverse is variance. So if the variance is large, then it means that the Gaussian will have can even have values away from 0, right? The W can have values away from 0, right? But if lambda is or lambda inverse is like very, very small, or if lambda is very large, then it means that the covariance of the Gaussian is like very small. The Gaussian spread is very small. It's peaked around. Okay, so let me. So suppose I have a Gaussian distribution, right? Right. With mean 0. So suppose this point is 0. Okay. So let me just. Right. So if this. Okay. So suppose I have some. Suppose my weight vector is drawn from a Gaussian distribution with mean 0 and some. I'm looking at a one-dimensional Gaussian distribution. Okay. So if so note that lambda inverse is basically sigma squared. Okay. Now, if lambda inverse is small, then it means that the variance. If lambda inverse is small, then it means that my Gaussian is like this. Okay. If lambda inverse is large, then it means that my Gaussian is something like this. Okay. So if lambda inverse is small, it means that the probability that W will take small values is very high. Okay. Okay. So if I make if lambda inverse is small, then it means that the Gaussian will be like more peaked around 0. Okay. So the lambda kind of tells us like how shrunk the Gaussian is towards zero. If lambda is large, then it means that the Gaussian is shrunk more towards towards zero, right? So it means that I am favoring more, the W to have zeros more aggressively. Okay. So I think it will become clear once I show you a picture of a one-dimensional case. So anyway, so our prior distribution on the weight vector is a Gaussian with mean vector 0 and the covariance matrix lambda inverse times ID. This is an identity covariance matrix. No, spherical covariance matrix. Okay. Now the same thing is that, now the next thing that you should keep in mind is that this multivariate Gaussian distribution, this is a d-dimensional Gaussian distribution because W is d-dimensional, right? I can write down this Gaussian distribution as a product of d many univariate Gaussian distributions on the individual components of the weight vector W. So this WD denotes the dth component of the weight vector. So this distribution can be written in a more simple way as a product of these one-dimensional distributions. Okay, what each of these, so this should now make more sense. It's saying that each component of W has a Gaussian prior with zero mean and a precision lambda or a variance lambda inverse. Okay, so again we are encouraging each WD to be close to zero. Okay, and how much we are encouraging it, that is dictated by what lambda is. If we set lambda too large, then it means that we are encouraging it more towards zero, right? Because then if lambda is large, then the variance is small, then it's like a Gaussian very concentrated toward around zero. So this prior distribution can be written as a product of these individual univariate Gaussian distribution. So again, just, yeah. Not necessarily, right? So that's a good point. So the thing is here I'm assuming that all these univariate Gaussian distributions have the same value of lambda, which is why I can write this product as this compact notation. But you can definitely have different values of lambda. For instance, if you want different components of W to be regularized differently, okay? Because you may want some Ws to be, so it's also related to feature selection. So you can definitely have a lambda d with every WD. So in fact, again, for simplicity, I'm keeping a same lambda, but there are definitely variants of this model where you can have different lambda on different components of W. Yeah. Yeah, again, so not necessarily, but again, just to keep things simple, we are saying that the covariance matrix on the prior is a diagonal matrix, okay? Or not even diagonal, it's a spherical case. If we have different lambda, then it will be a diagonal matrix. If we have a full covariance matrix, then it will be a more complex kind of a prior. But typically, a single lambda or different lambdas, like a diagonal, is fine in most applications. Okay, so let's move on. So here we have defined a prior, which can be represented as a product of these. So essentially, assuming that this spherical Gaussian assumes that different components of W are independent of each other. Okay, so which is why we can write it as a product of these individual Gaussians. Now we know what individual Gaussians look like, right? So again, this can be, so each of these Gaussians will have this form, right? Square root of lambda by 2 pi e to the power minus lambda by 2 times WD squared. So this is the expression of a Gaussian, okay? When we multiply all of these, we get the following, right? Again, the exponents get added up, right? So we have a sum over all the WD squared, right? Can we write it in form? So can we write this summation in form of W, this weight vector? So we can write it as W transpose W, right? This summation is the same as W transpose W, because if I take the inner product, it's nothing but the component-wise sum squared, sum, right? So we have seen that if we take this prior, P of W given, so I'm making the prior, explicitly depend on lambda. So I mean, I can choose to, not write lambda here, but I'm just mentioning it to show that this is a hyperparameter of the model. So our prior distribution is proportional to e to the power minus lambda by 2 times W transpose W. Okay. Let's also go back to the previous likelihood model that we saw, right? So our likelihood was P of y given x comma W was exp of minus beta by 2 y minus x times W transpose x minus y minus x times W. So this is our likelihood. We have seen that if we assume a Gaussian prior, our Gaussian prior looks like this. It's proportional to e to the power minus lambda by 2 W transpose W. Okay. Okay. And Okay, and as I was already mentioning, lambda denotes the precision of the Gaussian, which is inverse variance, and it kind of tells us how shrunk towards 0 WD is. Okay, so 0 is the mean of this Gaussian distribution. So you can think of, so I already drew this picture on the previous, on the workspace, that, you can assume that each of the components, so this is a overall distribution over W, but you can also think of the distribution on each component of W, which is a univariate Gaussian with mean 0 and the precision or variance controlled by lambda. If lambda is large, then it will be shrunk more towards the mean 0. If lambda is small, then it will be like fairly spread out. Okay. So as I was mentioning earlier, the zero mean prior is basically saying that we a priori expects our individual weights to have small values, okay? Which is related to this idea of regularization, because whenever we have a loss function with regularization, we use a regularization because we don't want very large coefficients, right? As you might have seen in the case of regression, linear regression, right? So, yeah, so this is very similar to adding a regularizer on the weight vector W, which basically promotes the individual components of W to take small values. Okay, and this regularizer, this prior might also remind you of an L2 regularizer. So, who has seen L2 regularizer in linear regression? I believe it would have been introduced. So if you think of the ridge regression, was it talked about? Yeah. So ridge regression is basically the least square objective plus an L2 regularizer, right? So what this probabilistic formulation showed is that if you use a Gaussian prior on the weight vector, it corresponds to an L2 regularizer. I mean, right now we have not fully worked out the detail, but it already kind of suggests that we have a term that looks like an L2 regularizer in the exponent, right? So when we actually write down the map solution, we will actually have that this term will pop out and we'll have a W transpose W, which is basically an L2 regularizer. Okay? So I'm hoping that you have seen linear regression and ridge regression, so you'll be able to connect how this relates to the linear regression solution. In fact, on the very first slide, I showed you both approaches, right? So if I go back, here is where so you have a loss function and you have this L2 regularizer, right? So in the regularized loss function formulation, we just say that, okay, let's use L2 regularizer, right? But in the probabilistic approach that I introduced just now, we saw that if we take a Gaussian prior on the weight vector, it kind of leads to this L2 regularizer, right? Because we saw that there was a term like W transpose W in the prior distribution. So let's go back to the, yeah. Okay, so now that we have seen the likelihood model and the prior, so again, both likelihood model and the prior both are Gaussian. Like likelihood model is P of y given x was a Gaussian. If you have forgotten that, then let me just take you to the previous slide. So P of y given x, well, it's not exactly, it's actually a Gaussian. It's a product of n Gaussians. In fact, you can show that it's a multivariate Gaussian. It's a multivariate Gaussian. E to the power minus a quadratic term. Okay, so likelihood is Gaussian. The prior is also Gaussian. So in fact, as we will see later, the posterior will also turn out to be a Gaussian, as we saw in the previous lecture. Because if likelihood and prior are Gaussian, then the posterior becomes a Gaussian. Okay, but we'll do that after a while. But we'll look at a few other things. Anyway, so we have defined the likelihood, we have defined the prior. So let's do some parameter estimation for W. Okay. First of all, we will do the maximum likelihood estimation, where we will not use the prior. We will only look at the likelihood. Fine? Yeah. Yes. Why? Well, so that's the idea of regularization, right? So if you are trying to learn, let's say, a linear model, right, where every feature has some importance, like given by the weight vector, the corresponding weight, right? So you don't want to give undue importance to a particular feature. So you don't want to make the weights too large, like, right? So you want the weights to have a reasonably small value, right? So that's the idea of regularization, right? So we are trying to achieve a similar effect in this probabilistic model by saying that the prior distribution on the weight vector or each component of the weight vector is a Gaussian with mean 0. So we are kind of saying that, well, all the weights are close to some mean 0, close to a 0 mean,